Okay, welcome back, everybody. Glad to see that there are still people interested in taking the class after the last lecture. You never know, maybe one year I'll give the first lecture and nobody will show up for lecture two. Uh, Today we're going to talk about so-called Bentley rules for work. But first, let me make a few comments. We didn't quite finish the last lecture. We'll post the remainder of the lecture, a video of it, in Canvas sometime tomorrow. And we'll also release homework 1 and project 1 later today. I'll hang around after class today to field questions for anyone who wants to join me. Okay, let's get going. We have a lot of things today. Today we're going to learn basic techniques for writing fast code. And we're going to start out with a 4-letter word you're all familiar with: work. So in performance engineering, the work of a program is all the operations it executes. You can think about it as the number of executed instructions. We don't like doing unnecessary work because that generally means our program is wasting hardware resources. So we try to reduce work. Generally, less work means faster code, but not always, because hardware is complicated. It's complicated, involving things like instruction level parallelism, caching, vectorization, speculation and branch prediction, etc. All of which we're going to learn about. But to a first order, reducing work is generally a good heuristic for making your code run faster and execute fewer instructions. Now, one way that you should all be familiar with for reducing work is algorithmic engineering, where you, for example, can get dramatic reductions in the work to solve a problem by using a better algorithm, such as when an n log n times sort replaces an n squared sort. And whereas most of the theory of algorithms concentrates just on the asymptotic behavior of a program, we're also going to care about what's hidden behind the big theta or big O. And today we're going to learn a bunch of other ways to reduce work. Okay, so these are all important methods, but today we're going to talk about things other than algorithms per se. So let's talk about how to reduce work. I want to go back a little bit in time to 1982. Many of the techniques for reducing work were originally codified by John Lewis Bentley. In 1982, about 40 years ago, he wrote a short little book called Writing Efficient Programs, which contained a list of rules. Now, some of his rules are also repeated in his other books. He wrote several other books, including probably his most famous is called Programming Pearls, which contain excellent lessons about programming that are still relevant today. The original Bentley rules dealt with more than just optimizing work, but work was pretty much the focus of most of them. Oh yeah, truthful disclosure, John Bentley was my PhD thesis advisor at Carnegie Mellon, where I got my PhD. He was actually only one of my PhD thesis advisors because I had two. The other was H.T. Kung, now at Harvard. So I come by my performance engineering pedigree honestly here. Several years ago, we wanted to update the Bentley original rules. So the course staff, formulated a new set of Bentley rules, all dealing with work. Today's lecture is actually organized as a set of 21 fairly independent mini lectures. We'll just quickly look at each rule and then move on to the next. Many of them are pretty independent. I don't expect you all to understand every bit of code that we're going to be looking at today in real time, But the examples are short and often clever, so you want to study them later so that you can use them in your own work. There are 4 areas that it covers: data structures, loops, logic, and functions. Actually, I think I do them in the order: data structures, logic, loops, and functions. So we're going to start with data structures. Now, data structures is how can you use data structures to improve performance? And the first idea, the first Bentley rule, has to do with packing and encoding. The idea of packing is to store more than one data value in a machine word. And the related idea of encoding is to convert data values into a representation that uses fewer bits. Broadly speaking, the idea is to use less storage. And bigger data typically takes longer to operate on and allocate, initialize, communicate, etc. So reducing storage can often lead to less work and faster code. Here's an example. In most computers, each character in a string is stored as an 8-bit byte, as you probably know. So a string such as September 3, 2020 can be stored in 17 bytes. It's actually 18 bytes because the compiler usually appends a null character to the end of the string to terminate it. So as you're reading through the string, you can read and know you got to the end because you have a terminator character, which is generally all zeros. And that's more than 2 64-bit words. So if you're going to move dates around a lot, you're going to have to move 3 words, 64-bit words or whatever, every time you need to move the date around. And computers tend to do a lot of moving of data. Now, assuming that you only store dates between 4000 approximately BCE and 4000 CE, there are every year 365.25 days approximately, and this is 8,000 years, so that ends up being around 3 million dates. In order to figure out how many bits we need to do that takes, we can just take the log 2, LG is the log base 2, the log 2 of that number, and of course we have to round up. And that ends up being 22 bits. This kind of calculation you can do pretty simply because if you just know a couple of conversions, the log of 1,000 is about 10 and the log of 1,000,000 is about 20. So here we've got the log of 1,000,000 times the log of 3. The log of 3 is about 2, so it ends up being 20 plus 22 is 22 bits, which easily fits in a 32-bit word. But the problem that you end up with is if you represent the dates compactly, it can be actually tricky to efficiently access the year, month, and day. So encoding isn't always the solution. Trying to get the fewest bits isn't always the solution. It's a trade-off. It all depends on how you're going to use the data. And so if it turns out you're moving data a lot, then this could be a very good way of doing it. If you're moving the data only some, maybe this isn't the best way because you're often extracting the year, month, and day individually. So the idea that we could have is to use packing rather than encoding to make extracting the year, month, and day easier. So here's a scheme that packs using what are called bit field structs. Each field in the struct is labeled with its size and the number of bits. So you just follow the field with a colon and the number of bits that you want for it. The C compiler generates efficient machine code to access bit fields. And if you pack the dates in this way, it turns out it only requires 22 bits, which will easily fit in a 32-bit word. But now it's really easy to pick out the year, month, and day. So that was a lecture. Next lecture. The next one is about augmentation. Okay, so the next technique, the idea is to use more storage to save time, not less. We just said if you use less storage, it often takes less time. Well, sometimes if you use more storage, it takes less time. Okay, it's a trade-off. So the idea of augmentation is to add information to a data structure to make common operations do less work. A good example is when you need to append linked lists. So suppose you have a singly linked list. Okay, typically for a singly linked list, you have a head pointer that points to the first element of the list, and then it has a field that points to the second element of the list, and so forth until the last element of the list contains a null pointer, doesn't point anywhere. Now, if you want to make one list, if you want to append one list to another, then you want to basically take the first list and replace the null pointer at the tail of the first list with a pointer to the head of the second list. And that involves walking down the length of the first list to find the tail of the list and then changing its null pointer to a pointer to the head of the second list. Now, you don't have to walk down the second list, but if the first list is long, it can be expensive to do that walk down the first list. So we can augment this data structure to make it operate faster. And in this case, what we'll do is we'll augment the list with a tail pointer. And now it turns out we can do the append operation in constant time. Okay? All we have to do is just access the tail pointer to get to the element that has the null pointer and make it point to the second list. Oh, we're not quite done. The new tail pointer for that list has to now point to wherever the tail pointer for the second list is. Okay? But it's a pretty simple operation and it takes constant time. Okay? You don't have to chase down to the end of the list. So that's a good example of augmentation. Next lecture. Let me see, do I have any comments on, so far no comments. So if you have comments, let me know. The next idea also involves using more storage, in this case to cache results so you don't have to recompute them. Oh, if you remove the tail in the linked list, how do you update the tail pointer in the head? Well, you're updating the tail pointer to go to the tail pointer of the second list. So you look at the second list tail pointer, and then you're going to throw out the header information for the second list typically. So the idea of caching is to store results. So here, for example, you have a program that performs a lot of calculations of the hypotenuse of a right triangle. And suppose that often it's going to ask you for exactly the thing you just asked for. Well, it turns out that square rooting the squirts, SQRT operator, is a relatively more expensive than multiplying and adding. It's roughly 2 to 4 times more expensive on modern architectures. So one thing you could do is once you've computed it once, is to put it someplace. And in this case, I've created 3 additional variables, cached A, cached B, and cached H. And what I do is when I'm asked, I check, oh, is this something I've seen before? Okay, if the thing that's being asked for is the thing I did previously, and then I just simply return the cache value. Okay, and otherwise, I go ahead and compute it, but of course, I also have to update the the cached values. So there's an overhead to it. So once again, this ends up being a good speed improvement if you hit the cache frequently enough. Typically, I think for this code, maybe if you're hitting it at least 2/3 of the time, it would be a faster way of doing it. But if you don't hit it off enough, then it may be a slowdown. So it's a trade-off. And of course, you can make the cache bigger. You can keep more elements in the cache than just one. So hardware isn't the only way to do caching. Software can do it. So yeah, so in dynamic programming, memoization you could view as an example of caching. Good. Yeah, so it's about 30% faster if you hit around 2/3 of the time. The next Bentley rule is precomputation, performing calculations ahead of time so as to avoid doing them when performance really matters. So let's say we need to compute a lot of binomial coefficients, what's sometimes called the choose function, n choose k. The formula can be pretty tricky to compute because the factorial function grows so quickly. In fact, it's super exponential, although not quite as fast as n to the n, but much faster than 2 to the n. And it turns out that if you're not careful, you can easily overflow the normal storage for an integer, which is typically 32 or 64 bits. So in the intermediate calculations, if you go ahead and try to compute n factorial, you're not going to be able to compute it very big, even though you're going to divide those out. And dealing with big numbers, if you do want to represent all those big numbers, that can take more work. So the idea is to say, well, how many numbers do I really need in my program to compute the choose function for? Maybe I can pre-compute them all and simply look them up at runtime. So that's going to be our idea. And we're also going to do a little bit of algorithmic engineering here and come up with a better way of computing the choose function than by computing the formula. And that's something that you're probably familiar with. It's called Pascal's triangle. So each element of the table is the sum of two adjacent numbers above it, in particular right above it and to the left. And so if you add those two things together, you can get it. So this code shows how you can compute the choose function. Okay, this is not pre-computation yet. This is just a better algorithm. If n is less than k, you return 0. Otherwise, if n is equal to 0, you return 1. Otherwise, if k is equal to 0, you return 1. And otherwise, you return the choose recursively of the two numbers above it. And of course, this is just like the question we had about dynamic programming and memoization. Why do this recursively? Let me simply compute this bottom up. So here's the code. So here we're going to say, let's say we're going to only care about choosing things that are 100 or less, okay, where n and k are both 99 or less. And so the function choose, we first of all have to initialize it, and we go through and compute n choose 0 to be 1 and n choose n to be 1. And now we run through all of the n and all of the k and compute this formula. And you can look at this formula in more detail later. So now whenever you need a binomial coefficient in the program, okay, you can simply index the choose array. You don't have to do any computation really except for a table lookup. It's really fast. Okay. Now this involves runtime initialization, and there's a way to actually make the compiler do this even before you start your program. And that's called compile time initialization. And it's another type of Bentley rule. The idea of compile time initialization is to store the values of constants during compilation, saving work at execution time. So here I've done it assuming that the size that I want to build of the table is of the Pascal triangle table is 10 by 10. Now I might go and type that in, but if it were 100 by 100, I think I would think twice about doing it. And that's where it can be really helpful to use another technique, which is the technique of metaprogramming. So the idea is that we can create a large static table by metaprogramming. Now, metaprogramming means writing code that writes code. You can metaprogram in any language. Okay, it doesn't have to be the same language you're coding in. So for this example, we're going to metaprogram in C, the same language we're coding in, so don't get confused. The metaprogram initializes the table with the actual computation and then prints out the actual C code that declares the table. So if you take a look at this, it's saying print F, int choose NN equals, whatever, and then continues through the code. I guess actually I have a bug here that I didn't realize, which is that I have to define N. So I didn't quite do that. So I'll correct that in the eventual slides. And so basically it's going through and it's printing out exactly the code. And then you can cut and paste, take a look at the output of this, cut and paste it into our real program, and voila, you have a compile time table of the right size. Okay, so you're basically writing a code that does it. Now, this is not always faster, surprisingly, even though you're computing it earlier, because the compiler now has to save all these values, and at runtime, it has to bring them in to primary memory from its disk system, from the file system. And that can be really, really slow. So usually, for a large table like this, it's actually better to initialize it at runtime with an init function, because then you can compute it at the speeds of primary memory rather than computing at the speeds of secondary memory, disk memory. But it's a trade-off. For small things, it can be quite, if you don't have very many of them, it can be quite worthwhile to compute things in advance. Is there a limit to how large we can make the table? There probably is. At some point, the compiler will choke on things. So the compilers are designed for human written code, and when you metaprogram, you will elicit compiler bugs like you've never seen, because the compilers are just not used to processing code written by other programs. So it's something you definitely have to be wary of, and definitely in your planning, don't expect that it's going to work right necessarily the first time. And
there actually are.
It also means that the the binary is going to be bigger.
I was just going to add that there are ways aside from generating C code that you can also generate binary data that gets embedded in the program that can scale to somewhat larger sizes than the C compiler could easily handle.
Great. Okay, so But the idea is you could write this program in Python. So Python is a perfectly good metaprogramming language. Okay, use Python to write your code. And what's great is that for a lot of things, if you can use it, if you can parameterize your code and have it write it, you can do that in a way that you're guaranteed that it's going to be correct no matter what values you end up putting in there, because you've already debugged the Python code to do the right thing, to print out the right stuff. Okay, next lecture, sparsity. The idea of sparsity is to avoid storing and computing on zeros. The basic idea is that the fastest way to compute is not to compute at all. And here's an example. So suppose we're doing this matrix vector multiplication. So I hope people remember matrix vector multiplication. It basically runs through every element of the matrix, so in this case 36 entries, and multiplies it by the appropriate element of the vector and adds that into the output in Y. So this is basically 36 multiply adds. But this particular matrix has 22 zeros. And it turns out zeros, we know how to multiply zeros without actually multiplying. Why bother multiplying by zero? I know what the answer is. I don't even have to look at the matrix. Okay, and if I have to add in a zero, why add in a zero? I know what the answer is. I just don't add in. So let's start out by removing all the zeros. Okay, and now we're left with 14 non-zero entries. So one of the tricks of sparsity is, once again, goes back to the idea of let's use less space. Okay, so we can store these things more efficiently by not storing all that empty space. We only store the things we want. And here's one of the most common ways of representing a sparse matrix efficiently. It's called compressed sparse rows, or CSR, and it is used for many sparse matrix codes. So the idea is there are three arrays. We're going to start at the bottom with the vals array. Okay, so the vals array simply has the non-zeros in each row just listed. So for example, the first row has only two non-zeros, 3, 1. So those are the first two elements. The second row, or the zeroth row, I should have said, the first row has 4, 1, 5, 9. Okay, and that's the one I've highlighted here. And so forth, 2, 6, 5, 3, etc. So the vals just has that. And then the calls array says what column is each of those values in. So the value 3 is in column 0. The value 1 is in column 4. Okay, the value 4 is in column 1, etc. So that's what the calls array is. And now the rows array basically points to the beginning and ending, or the beginning of every row. Okay, and so for example, for row labeled 1, the 2 says that that row begins in column, begins in with that element, okay, in position 2. So it's and it ends at the beginning of the next one. So you can, from the rows array between 2 and 6 minus 1 or 5, you can find all the elements of row 1 consecutively. Okay, and the same is true for the others. So, so for example, row 3 occupies the positions from 8 and 9 up to but not including 10, and so forth. Okay, so that's and so now the storage here ends up being n for the rows plus twice the number of non-zeros instead of n squared. So if n squared is really big and the number of non-zeros is relatively small, this is a more efficient way to store things. So typically, it's pretty good when you've got at most 10% of the elements are non-zeros. So that's a fair amount of sparseness. Then this tends to be a really good representation. Now you still have to operate on it. And so the code here goes through, and if you analyze it, you'll see that the number of scalar multiplications is the number of non-zeros, which is potentially much less than n squared. So it's a really fast. I'll let you study this on your own. It's a little bit more involved than the doubly nested loop for dense matrix vector multiplication, but it's not too bad. And typically you need the matrix, as I say, to contain 10% or less for a sparse representation to pay off. Fortunately, most matrices in practice have this degree of sparsity or even less. So this is really a very, very common way of representing matrices for large data sets. Now you can use the same trick on graphs. Okay. Here we've used it. I haven't stored anything in the graph. I've just stored the edges. But the idea is that you use the same idea, that you're keeping the offsets and the list of edges as regions in the edges array. And then if you have edge weights, then you can make an additional weight array or store it in the record for a record that contains both the edge index and the edge weight. And in fact, the reason this works is that that a sparse matrix and a graph are essentially the same thing. They're pretty much isomorphic. And you can take a look at this and so forth. So that completes our first collection of things for data structures. These are techniques that apply in a lot of other circumstances. So let's move on now to the Bentley rules for logic, for program logic. Okay. The first one is what's called constant folding and propagation. By the way, many of these logic ones are used in compilers. So compilers will often do many of these things already. And the reason you'll want to know them is because the compiler doesn't always do it. And also, if you look at the code generated by the compiler, you'll want to understand what it is doing. And when you code, you want to be able to code with these things in mind so that the compiler can optimize things for you. So you don't have to, because you've used a style that promotes these kind of logic rules. And constant folding propagation is one of the most effective things that a compiler does. The idea is to evaluate constant expressions and then substitute the results into further expressions and then keep simplifying that all during compile time. So here's an example. Okay, here we're building a digital orrery. What's an orrery, you say? I'm glad you asked. Okay, here's a mechanical orrery. They used to be quite popular in the Renaissance. An orrery is a model of the solar system. And they made them that would have the, it was actually the difficulty in building an orrery where the Earth was at the center that led everybody to realize, led Kepler and others to realize, oh, really, the sun is at the center. That makes the mechanical thing way easier. So in the code here, the radius of the Earth is constant. Okay, it's about 6 0.371 million meters. And so when you compute the diameter as being 2 times the radius, rather than you having to calculate what's twice that number and put that into your code, you can simply ask the compiler to do it, and the compiler will do that at runtime. And it'll compute the circumference, because that, now you have the diameter, and so you can write very clear code that at runtime will always be, all the constants will be folded and propagated to other expressions that require any of these terms. Okay, and so you won't have to, when you access those things, you won't have to operate. Now, typically these will be evaluated during compilation as long as the compiler optimization level is set high enough. So the compiler has a bunch of flags, compile time switches, that typically go from -0 to -03, where 0 means no optimization and -03 means high optimization. And I believe that most compilers, constant folding and propagation only requires -01 for it to do. The reason you might like to have -00 is so that you can see everything in detail. It's much closer if you're looking at the output to the to what you actually coded, because these optimizations haven't been done. And for running, you'll really usually want something like -03. Okay. But sometimes, if you're trying to understand what's going on, let's say you have a bug in your code and the code works correctly under -00, but incorrectly on -03, you may want to try some of the other optimization levels to see where the compiler bug is arising. Good. Yeah, so with sufficiently high optimization level, -01, for example, these are evaluated at compile time. And I see that, yes, there are some really old orreries. Can you take advantage of sparsity for dynamically computed matrices? Yes, so often you can just generate the non-zeros. Often what you're doing, for example, if you look at the matrix that corresponds to a two-dimensional mesh, everything is connected to just 4 neighbors. And the sparse matrix for that, you never have to even look at the other things. So yeah, often you don't need to compute every element to see that it's 0. You know from the logic of your code that it's already 0. So you simply create something that's sparse. Okay. And the constant keyword is not technically necessarily always, but it assures the compiler and it assures you that you expect that to be constant. So sometimes the compiler can get confused with things, especially if you have intermodule access. It may think that it's a variable, that it might be set somewhere else. And if it thinks that the value might change somewhere, then it won't do this constant folding. But if you declare it as const, it says, I assure you I'm not trying to change this anywhere else. So yes, use consts liberally. You'll have much faster code. Okay, next lecture. Common subexpression elimination. Once again, the compiler does this really, really well, but not always, and sometimes you need to do it. So the idea of common subject expression elimination is to avoid computing the same expression multiple times, and you do it by evaluating the expression once and then reusing the result when you need it later. Here's a really simple example. Okay, so suppose that I have this straight line code. So A equals B plus C, B equals A minus D, C equals B plus C, D equals A minus D. Now, if you look at this carefully, you see, oh, B is computing A minus D, and D is computing A minus D. So why not rewrite the code to just simply assign D to be the value of B and save one arithmetic operation? Okay, pretty straightforward. And I'm computing it twice, don't compute it twice. Okay, that seems like a waste. Okay, something that the Department of Redundancy department would likely do. What about the assignment of B plus C to A? Can we just replace it by C equals A? Well, no, because I changed the value of B in the second line. And since I changed the value of B, C is actually getting a different value, so replacing it would be incorrect. The compiler is really clever at figuring these things out, and it can figure out those kinds of simple cases. But for more complex cases, it may very well be up to do. We will teach you how to read the compiler's intermediate representation so you can see whether the compiler is doing what it's supposed to be or whether you need to intervene somehow. Okay, sometimes you'll say, gee, I folded all these things and nothing got faster and it should be faster. And then you look at your output and, oh, nope, it's not doing common sub-expression elimination. Oh, I see why. I actually changed the value here. It's not the same thing. Okay, I can rewrite my code a little bit and now enable that. So that's the kind of thing you'll be able to do. Okay, the next lecture. Algebraic identities. The idea of exploiting algebraic identities is to replace expensive algebraic expressions with algebraic equivalents that require less work. Okay, so it's basically using math. So here's an example of a code that's going to determine whether two balls intersect, okay, whether they collide. We're going to compute the distance between the centers of the balls and compare it with the sum of the radii. Okay, so if the distance between the two centers is less than the sum of the radii, hey, then they intersect, then they collide. Okay, so here's some code that does it. This calculation involves the square root of the sum of squares of the coordinates differences. That's what's going on in this code here that has the square root. And then it compares, it returns a true or false by comparing whether D is less than or equal to the sum of the two radii. Now, as I mentioned, the square root is typically 2 to 4 times the cost of a multiply on modern architecture. So if your code is doing a lot of collision detection, this could be suboptimal. Okay, so the expensive route, the routine is this. Now, the algebraic identity we're going to use is pretty simple. Okay, for positive numbers, the square root of a number u is less than or equal to a number v exactly when u is less than or equal to v squared. And v squared is a lot cheaper to compute because it's just a multiply. So we can rewrite the collides code to make the computation cheaper, okay, using the square. Okay, and so now I'm comparing, rather than taking the square root of d, I've computed d squared, okay, avoiding the square root, and then return whether the square is bigger than the square of the two numbers here, okay, where square simply returns, x times x, okay. Now, you have to be a little bit careful here when you use algebraic identities when you're doing floating point, because floating point doesn't obey the real number axioms. And in particular, floating point operations are not associative. Okay, so remember the associative law. It says that the quantity A plus B added to C is the same as A added to the quantity B plus C. Okay, and that turns out not to be true for floating point operations because of round-off error. So you've got to watch out about applying this rule with floating point numbers, because it's very easy to end up with a very inaccurate result if you don't pay attention to your numerics when you when you apply algebraic identities. Okay, but it is generally a really good strategy to use the algebraic identities. The next technique, we're going to use pretty much the same example. And the idea here is to what's called creating a fast path. So here's the original code. And it involves this, a bunch of differences and a bunch of squares and then a comparison. And the idea is to do something a lot simpler, which most of the time probably gives you the right answer. And that is to compute a bounding box around the balls and compare those. Okay, because a bounding box doesn't require any calculation to see whether or not that's just one of the coordinates. So let me just show you the code here. Okay, so what we do is the fast path is to just look at the absolute value of the difference. Okay, and of the x coordinates and compare that to the two radii versus the absolute value of the next, etc. Okay? And if any of those ends up true, before I even have to go squaring and stuff like that, I can, fail out very quickly and return false. And then if it turns out that none of those apply, well, then I go and do the more careful calculation to return the actual answer. Now, it turns out for this example, probably not worth it, okay? But graphics applications use this bounding box fast paths technique all the time, and there are a lot of other cases where doing a bounding box is a good strategy. This technique also illustrates a related problem. Oh, also, by the way, notice that there's all kinds of common sub-expressions that you can eliminate here, that the compiler will eliminate for you. Okay, so not all the work in computing the absolute values is wasted. There's another related strategy, which is called short-circuiting. And the idea of short-circuiting is to simply stop evaluating as soon as you know the answer. So here's a code that adds up a bunch of numbers and then asks whether that sum exceeds a limit. So we can potentially optimize this code, since all elements are non-negative, by testing along the way whether you've exceeded the limit. And if we expect that most of the time we're going to exceed the limit, we can short-circuit the full loop and return without completing all the iterations, saving a lot of work. Of course, there's more work done in the loop, okay, because we've now added an addition. In addition to the addition, we're also adding a comparison and a test. Okay, so it's not necessarily faster, but there's a trade-off there. Okay, for certain things that take a lot of computation where it's likely to fail early, this can be a really good strategy. There's another one that is also similar to that, which is ordering tests. So the idea is, suppose you're doing a bunch of tests, a sequence. You do test 1, test 2, etc. The idea of ordering tests is to perform those that are more often successful before tests that are rarely successful. So here's a code. This code, it used to make sense to do this optimization. Today, the compiler does so much better job, it doesn't really pay off. But the idea is, suppose you want to test whether a character is white space. Now, the white space characters are carriage return, tab, a blank space, and a new line. And so this code just simply tests them, and it uses the double bar operator, which is the short-circuiting logical operator. This is the operator that quits as soon as it finds the first case. And yes, compilers do short circuit. It doesn't necessarily short circuit their computers also short circuit, but that's a different problem when their power supplies go out. So here it's basically goes and compilers will short circuit expressions if it can figure out that it's able to do so and it's productive to do so. So here, the most common character that's white space is a space, and the second most common character is a new line. Okay, so we should order those first and then tab, and then we rarely see the naked carriage return character. So this isn't going to necessarily be good today compared with just letting the compiler do what it wants to do, but it illustrates the technique of ordering tests. Now there's another strategy, which is the idea of combining tests. And once again, I'm going to give you an example that probably isn't the way you want to do it, but I use it because it actually came up. I was working a while ago on a program where, and to keep the long story short, the functionality of a full adder had been implemented in software. Now, a full adder is a hardware device with 3 Boolean inputs and 2 Boolean outputs. So 3 bits of input, 2 bits of output. And here's the truth table for it. Okay, here's the code that was being used to encode this table. Okay, so here's a full adder. It has 3 inputs, and it's going to produce 2 outputs. So it produces them as having writable output values. And so it says, if A is 0, then if B is 0, then if C is 0, then the sum is 0 and the carry is 0. Otherwise, meaning C is 1, then the sum is 1, the carry 1, and so forth. So it's this convoluted net. I mean, it's like check to see if this is correct, right? It blows my mind just trying to see if it's correct. But also it has 3 levels of nested conditionals. And it turns out, as we'll learn next Tuesday, conditional branches can be remarkably expensive. Okay, so one way to improve this code is to combine all the tests into one. And here's the code that does it. We basically compare A to 1, and that returns a 0 if it's true and a 1 if it's true and a 0 if it's false. Okay, and we then pack that into a word with B. We left shift it 2, pack that into a word with B, which we left shift 1, which we pack in with C. And so when we're done, the variable test has a 3-bit value. And now we just switch on the values. Okay, so we do, if the case is 0, it means the sum is 0, the carry is 0. If the case is 1, it means the sum is 1, the carry is 0, and so forth. And now we can see this a lot better, and this code will generally run faster. Okay, now in this case, this is also a terrible way to do it because the outputs can be computed mathematically. Okay, I can do a bunch of simple operations on A and B. In particular, For those who remember your hardware class, the sum is the parity of the 3 bits, that is the number of ones, whether the number of ones is even or odd, and the carry is the majority. Are there more zeros or more ones? And so it's much easier to implement that directly. But sometimes you can combine tests and do a table lookup, for example. Don't even write the code at. You just simply index a table on the result of it. And we'll see some examples like that. So it also helps to understand the logic rules to understand what the compiler is doing. Okay? So even if you're not doing it, knowing what the compiler is doing helps you look at that code. Okay, let's move on to our next collection of operations, next collection of rules. And this is loops. So first, let me take a second and say why we do loops, okay? They're often the focus of performance optimization, okay? And the reason is pretty straightforward. Loops account for a lot of work, okay? So let's consider this idea. Suppose that you have a 2 gigahertz processor that can execute 1 instruction per clock cycle. And suppose you have a program that contains 16 gigabytes of instructions, but is all simple straight line code. In other words, no backward branches, which is what you need to implement a loop. Okay, so 16 gigabytes is what you might find on a laptop, for example. Okay, but there are no backwards branches. Okay, there are no recursive function calls that'll take you to somewhere earlier in the code. How long does this code take to run? Well, that's basically just the worst case is that you just run through one instruction to the next. Okay, and if you calculate it out, it's 16 gigabytes divided by 2 gigahertz, and that's at most 8 seconds. Now, as you know, most programs spend longer than 8 seconds. So therefore, they tend to execute instructions more than once, okay? And most code spends most of its time, one way or another, in loops. And that's why we focus on them. So let's just take a look at loops just to remind you what happens when a loop runs. So here's a simple loop. It's basically adding up, it's not basically, it is adding up the elements of an array A, okay? The loop control is the part within the parentheses here that says start the index at I, increment it, that's the third time, each time through the loop, and don't go beyond I bigger than N. Now, if you look at how this actually gets executed, okay, so this is kind of a pseudocode for loop execution, okay. Basically, it starts out at the top and initializes sum, then it sets I to 0, and then it does a test to see if I is greater than or equal to N, and if so, it goes to loop exit. Otherwise, it adds in A of I, it increments I, it checks to see if I is greater than or equal to N. If it is, it goes to loop exit, etc. And so this is what's going through. So you can see that in addition to executing the body of the loop spends a lot of time executing loop control. Okay? So it's not just the calculation of the sum, but also a comparison and test in the loop control. And that may not seem like much, but it can add up. So a lot of things deal with either things in the loop or dealing with loop control. The first one we're going to talk about is the most basic one, and it's the idea of hoisting, sometimes called loop invariant code motion. And this doesn't deal with the loop control, it deals with the body of the loop. The idea is to avoid recomputing things every time through the loop. So for example, suppose we have this simple piece of code. Here we're going to scale the vector x, okay, by this complicated expression, okay, the exponential of the square root of pi over 2, okay. Now it turns out if you think about it, that every time through this loop, we're computing this expensive operation. And exponential is expensive and square root is expensive. Okay, so we're computing that every single time through the loop when that value never changes. So I can improve the performance of this loop pretty simply. I simply compute this scaling factor before I enter the loop, and then I simply look it up, okay, and use it in the loop. Now, the compiler will actually often do this if it can figure out that that expression is a constant expression. For that, it has to know that square root and exponential are both constant functions, okay? And if they're in separate compilation units, it may not be able to figure that out without an explicit declaration. So sometimes you have to do it. So this is very simple and expressive. We get stuff out of loops. Okay, that's a basic rule. There is one time where you don't want to pull things out of loops that compilers sometimes have a hard time dealing with, which is when you expect the loop to execute 0 times. And this is often the case for error checking. You will do a calculation, and then it'll return an error code. And while that error code is not the right code, you do it again, okay? And usually you expect it's not going to error. And unfortunately, sometimes compilers get confused by that. But for most of what we're going to be doing, move stuff out of loops, because most loops are executed, 2 or more times. Next lecture, sentinels. So sentinels are special dummy values placed in a data structure to simplify the logic of boundary conditions, and in particular, the handling of loop exit tests. So this is a way of trying to deal with the loop control and the way it interacts with tests that might be within the loop. So here's an example. We're adding up the elements of an array and storing them into a sum. And we're going to detect whether or not that sum overflows. So normally, if the elements are non-negative and I add in, I should get a value that is of sum that is strictly bigger than the thing I added in. But we actually deal with finite size integers, in this case 2 to the 64th. Okay, so uint 64 underscore t means an integer of 64 bits that's unsigned. And when we add it up, we will end up with, if something is very close to 2 to the 64, we'll add it in, we'll actually get something that is much, much, much less than the thing we added in. So that's how we know we overflowed, okay? And so this is a code that tests whether the sum of the values in an array will overflow, okay? Now, here we have to make 2 tests. We have to compare I with n, and we also have to compare the sum with a of I. Okay, so that's 2 tests that have to go on. And as I say, comparisons can be expensive. Okay, so here's the rewritten code. What I've done here is I've put 2 elements at the end of the array, okay, at positions n and n plus 1. So you need to have that they exist and can't be clobbered. And now it turns out that you can omit you can do just one comparison of sum with AI, because if I is less than that termination condition will also cause this while loop to end. And so you save one test. So this logic is a little bit tricky. I don't expect you to understand it now, but take a look. Okay, the next strategy is called loop unrolling. Now, loop unrolling attempts to save work in the loop control. by combining several consecutive iterations of a loop into a single iteration and reducing the total number of iterations of the loop and consequently the number of times that the instructions that control the loop have to be executed. Okay? And there's two types of loop unrolling. Full loop unrolling, where you simply unroll the loop and the loop disappears, and the other is partial, where several but not all of the iterations are unrolled. Typically, you'll see mostly partial loop unrolling. We'll talk about both. Okay, so here's an example of full loop unrolling. On the left here, we have a code that simply adds up 10 numbers in the array A. And in the right, we add up the numbers. And as you can see, we're doing a lot less work because on the right-hand side, because there is no loop control. Now, the downside of this possibly is that I have made the code be bigger. And one of the things that can happen is that you can, the computer has an instruction cache, and loop unrolling can put a lot of pressure on the instruction cache. So it's not necessarily faster just because it's executing fewer instructions. Okay, in this case, it's likely to be faster, but not necessarily. Okay, longer code can do things. And yes, compilers will do loop unrolling automatically, and there is a compiler pragma or suggestion to the loop where you can say, please unroll this loop, and here's how much I think you ought to unroll it by. Okay, so the other thing about this unrolling is the loop control is completely gone. The compiler can actually do this automatic. The index I doesn't exist on the right because of constant folding and propagation, which is one reason loop unrolling is effective. It often enables other optimizations like constant folding and propagation, subexpression, common subexpression elimination, and so forth. Those things can be enabled by loop unrolling. There should be, to answer a question in the Slack, there should be no difference in principle in whether you unroll or the compiler unrolls. Okay. Usually you want to let the compiler do it because you want your code to be simple and clean and readable. But if the compiler won't do it, then you have to try it out and then see whether it's actually faster or not faster. Sometimes the compiler won't do it. Or you can try to do it manually even if the compiler is doing it. But first look to see what the compiler is doing. Okay, and we'll teach you how to do that. Okay, partial loop unrolling is a little bit more complicated because you still have the loop. So here, the loop has been partially enrolled by 4. Okay. Here you can see the impact on the loop. The loop index now is skipping by 4. Okay. Now, you can also see it's a little tricky sometimes to get the termination conditions just right. If the compiler does it, it'll get them right. Okay. If you do it, okay, maybe you'll get it right. Okay. So it's more time. And one of the things you're going to have to optimize for these projects is to do the projects in the allocated time. You will need to optimize your own time and make sure that you're spending time on things that matter and not on things that don't matter. Okay, so the benefits of loop unrolling is there are fewer instructions devoted to loop control. It enables more compiler optimizations. But as I mentioned, if you enroll too much, it can cause poor use of the instruction cache because the code size is bigger. Okay. The next lecture is loop fusion. So the idea of loop fusion, which is also called jamming, is to combine multiple loops over the same index range into a single loop body, thereby saving the overhead of loop control. So compilers can do this. This can be a lot trickier for compilers to do, and they don't do it nearly as well as they do unrolling. So here's an example. we're going to merge these two loops. Each strides through the elements of A and B. The first computes CI to be the minimum of A and B, and the second computes the maximum. Okay, so this syntax here is the ternary if-else operator. So if you take a Boolean expression, question mark, one value, and the next value, it says if that Boolean is true, do AI, otherwise do BI, but it does it as an expression. Okay, so in this case, they're both going through. One is computing all the mins, the other is computing all the maxes. Okay, and storing that the mins into C, the maxes into D. Okay, these two loops can be fused. Okay, and or jammed. So here we go once through and we do a comparison. And notice here that now the compiler can perform more optimizations because there's common sub-expression elimination. I'm doing the same comparison between two elements. It also gets better cache behavior, as we'll see later, because it can bring AI and BI into cache and then do two things with it in storing C and D, rather than bringing AI and BI, storing out C, and then having to do it again. So it actually saves on in cache behavior. Okay. The next loop optimization is called eliminating wasted iterations. And the idea is to modify loop bounds to avoid executing loop iterations over essentially empty loop bodies. And I can't believe how often I see people writing loops, sometimes ones the compiler can't figure out. So here's an example. Okay, this is a code to transpose a matrix. So the idea is to swap Aij with Aji. So the inner loop does the swap operation, okay, which you've probably seen, but maybe you haven't. You know, store Aij into a temporary, put Aji into Aij, then put Aji, back in. So you go through this, and if you're not careful and you don't have this I greater than J statement here, you can discover that all you've done is a very expensive identity computation. You know, you swap I with J, and then, you swap Aij with Aji, and then the loop swaps it back, okay, because you did it both times. You have to check that I is greater than J. But this turns out that half the iterations of this doubly nested loop don't do any work. They just simply do the test and then do it. So you can replace that fix that by replacing this code to eliminate the iteration. So here what we did is, rather than testing J less than N, we make J be less than I. And now we only go through the iterations, and we save half of the iterations as being, only loop overhead. And this is definitely an optimization worth having done. Okay? So we simply restrict the range, and now the code is more efficient. The last collection of things of Bentley rules deals with functions. Functions are great for abstraction, but they can have big overheads. The principal way of getting rid of function overhead is the idea of inlining, to avoid the overhead of a function call by replacing the call to the function with the body of the function itself. So let me illustrate here. Here's a function that sums the squares of the values in an array A. Okay, just goes through and computes the squares. It calls the subroutine square, which simply multiplies its argument by itself. So in addition to actually squaring it, it has to call the square function. So we can optimize away this square function, okay, by simply creating a temporary for AI and then adding the two things. In fact, the compiler probably creates the temporary if you just wrote AI times AI in here. Okay, and it saves the overhead. You can inline functions by hand, but that typically makes the code messier and harder to maintain and debug. Instead, what you want to learn how to do is to convince the compiler to inline functions for you. Okay, so the idea is you can do that by using this keyword inline, okay, to ask the compiler to inline for you. Now, sometimes you can ask it to do it and it won't do it, and sometimes it will do it and you didn't ask it. Okay, generally, you can get around it when it really doesn't want to do it by using the attribute feature, which we'll learn about, and using the attribute always inline if you want to be sure it inlines a function. But normally you can just suggest that it inline it. And usually you only inline static functions. Static function is one that is local in scope. But not always. Sometimes, but almost always, you'll find that you're writing static inline. So inlining is, by the way, better typically than using macros, which do a textual expansion, because a function evaluates its arguments before executing. So, for example, if this square function were calling something simpler, more complicated than a of I, if you did a macro for the square, then it would go through that calculation twice. Whereas if you can get it to inline, the compiler is smart and it'll only do it once, just as it does when it calls the function. Okay. So inline functions are generally just as efficient as macros, and they're safer to use and better structured. So I highly recommend you use inline functions. Okay. The next operation is tail recursion elimination, and it happens for recursive codes when you remove the overhead of a recursive call that occurs as the last step of a function. In that case, the call can be replaced to a branch to the top of the function, and you can reuse the storage. Okay, so this is a little bit complicated. I don't expect you to understand everything right now, but let me go through the example, and you can study it later. This is something, by the way, the compiler will almost always do for you. So here's an example of quicksort. Okay, quicksort calls the if it's not a trivial problem to solve, calls the partition routine that returns an index for which part that it has partitioned the smaller elements and the larger elements around. Okay, and then you quicksort the first part of the array, and then you quicksort the second part of the array. And here I'm doing a little bit of a C trick, which is that if you pass an array as the start plus a value, it actually treats the array as starting in that position. And it enables you so that in your code, you only have to deal with one limit. You can always index things from 0. It's really it's one of the C puns, and you should take a look at it because it's very common in C code and also can be more efficient. So it basically, but the important thing here is that it calls itself recursively. Okay. So and that involves creating a new activation record for the local variables, pushing them on the stack, and all the things that is needed that you learned in your architecture class for executing a function. So here's the function that is the tail recursive function. And we want to get rid of it. We branch up to the top, and there's a branch that says right now if n is greater than 1, that gets converted into a while loop. And instead of, before we do the branch, what we do is we say, okay, we've done this particular invocation, so now let's set up the local variables to be the local variables for the recursive call. And now I go up to the top. And so the impact of that is that there's only one recursive call in the function, and it's faster because it doesn't go through the need of pushing a whole bunch of frames on the stack, which when it returns will simply be popped off. It pops them off before the call, if you will, rather than popping them off after the call. Okay. Coarsening recursion is the idea of increasing the size of a base case and handling it with more efficient code that can avoid function call overhead. Okay, as you'll see when we give you the conclusion of lecture 1, we use that in in the matrix multiplication algorithm. Okay, so so in this case, what we've done is we've replaced the base case with a with a different sorting algorithm, but even sometimes inlining the original code can be a good strategy. But the idea is, rather than going down to n is 1, just go down to some threshold, and below that threshold, okay, then you do the base case of the recursion. So it takes all those tiny recursive calls and combines them into, something that's coded more efficiently. Yes, so compilers will automatically convert tail recursion to loops. Yes, indeed. Okay. Yes, indeed, for the question on Slack. Okay. Yes, they will. And they usually will do this optimization, I think, even at, I'm not sure if it'll do it at 01, but it very likely may do it at 01. Okay, that was 21 lectures for the price of 1. So I always thought that our speed limit infinity applied to code, not to the lecturer. Whew. But I did it. Okay. Just to summarize, here are the things that we looked at. Okay. There are a lot of them. They're little. Okay. They're each a different technique. Okay. Let me close with a little advice. Avoid premature optimization. This is Knuth's advice. First, get correct working code, then optimize, preserving correctness by regression testing, not a regression testing, by regression testing. Okay, so the idea is you want to maintain the invariant that your code always works, and the way to do that is to test it and keep adding to the tests. Whenever you find a bug, you add a test to your test suite, and you do that before you correct the bug. Then you test that your code fails your test, and then you correct the bug and verify that it now passes. And when you test future things, you always run through the old tests, because studies have shown that the vast majority of vast majority of bugs are bugs that occurred before or would be caught by a test that you did before. Okay? So preserve correctness is one of the most important things you can do to get fast code. Okay? Because otherwise you'll discover that your great creative fast idea just doesn't work. Okay, reducing the work of a program does not necessarily decrease its running time. Remember that, but it is a good heuristic. Okay, and it's definitely worth looking at. There are a lot of other things. Many optimizations involve trade-offs. Okay, in homework 2, we'll look at using a profiler to see what homework needs to be optimized. Okay, and so you can see more graphically where time is being spent by the program. Don't waste your time on code that isn't executed very often. Leave that clean and inefficient, okay? And the compiler automates many low-level optimizations, but not all, and we'll see how to look at the compiler output in upcoming lectures, okay? And finally, if you find during your things, every term, somebody finds an example of work optimization, or other kinds of optimizations for that matter, that the course staff has never seen before, or that points out a really neat and clever thing. Okay, if that happens, please let us know. We're trying to collect these things to share with everybody. Okay, share it you'll get participation points for sharing it on Piazza. Okay, really, really good. Okay, that completes the lecture. I will hang around for a little bit. We'll enable everybody's to unmute, and anybody who'd like to ask questions orally, I'd be happy to field them. Okay, so thank you very much, and good luck on homework 1 again, and project 1 will be going out